welcome to everybody to the Lunch and Learn with the Commercial Smallsat Data Acquisition Program, subject matter experts. We've had this program for a while, and it's going to be, I think, really nice to be able to hear from some of the folks that have actually been using the data related to the quality and their findings of these commercial products. So we got a really good slate of folks today. We've got Eric Vermote, who will discuss, the accuracy and that type of thing. We got Gary Lin and Bin Tan, sorry, discuss some of the geolocation things, and Alexei Lyapustin.
So, presentation mode?
Yes.
Okay, thank you. So I'm going to give a brief presentation about the planet data calibration evaluation. I mean, it's a little bit more than calibration, but calibration is kind of driving the whole data quality. So that's a really important step. I mean, just want to remind you where we use the data for looking at long-term data set, trying to build the land climate data record, and we started that work with Avi Chira with the data from 1982. Of course, I start later in about 1991 to work on the data set, and the first thing I work on was the calibration. So, and I'm still working on calibration, and I think everybody does that kind of work. And this is good. I mean, of course, there's a bias here, and I don't have time to go into explanation of this today, but maybe another time. And if you look in detail on a monthly basis, this is, for example, the comparison of a band-managed site, Aqua versus Terra for December 2018. So this will give you one point of the what I showed before, the time series, but there's much more information. There's information about the scatter. We can analyze noise and things like that. You notice that we have a large dynamic range. I mean, we try to maximize and not only focus on bright side, but get really what people are looking at. So from vegetation to bright side. So more than 400 sites. I mean, at first, when I was asked to look at the planet data, I remember downloading the data was quite challenging. It's still challenging, but it's been getting better. But nevertheless, it's still a lot of work just to download those 400 sites. So we start doing a prioritization of the site to look at the one who was the most favorable for intercomparison. So here you got the signal, and it's hard to see, but the red crosses is from all the 400 plus sites, and then we select. We classify the site by how good they are in terms of correlation, in terms of stability, and so on. And you could see like here with 10 sites, which is the black cross, you already reproduce very well what you're seeing with all the sites. This is just a joke here for one of my co-worker, but and 50 sites really give you a very good representation. So we went ahead and we apply to planet data that approach, and so for the first evaluation, we had a selection. We download as much data as we could over 6 months. I mean, 6 months of acquisition from January 2019 to end of June 2019. So actually 7 months. No, 6 months, sorry. And we got 67 sites, and this was the 67 best sites. And as you could see, there's a lot of them which are over. There's and some of a vegetation, but a lot of a arid area. Nevertheless, so we had to derive to look at surface reflectance, of course, and we first compared the planet product for surface reflectance and some of the in-house atmospheric correction, where we use the MODIS aerosol optical thickness as a shortcut to correct the data, and both methods were evaluated and compared, and no major difference were found. So we went ahead and applied our own corrections, since it was very equivalent to what the Planet folks were doing, and satisfactory given the limitation of the instrument spectrally and so on and so forth. We found some problem with cloud contamination, so we had to use some kind of in-house cloud mask, very simple one. But since we were looking at the same site all the time, we were able to do some reasonable job by looking at a simple threshold in the blue band to filter out cloudy data. So the first result from this whole data set, so for this first data set, at the top you got Terra versus Aqua, both in the red and the near infrared. And this is what you would expect to get if things were working as it is for MODIS. And on the bottom you got the planet versus Aqua, near infrared and red, and you notice that even if the slope is kind of reasonable, so it's only a 4% bias, that there is much more scatter just visible in the cross comparison. So we can analyze furthermore and look on the monthly basis at the difference between the planet and Aqua. And what you notice now, it's that it's pretty stable with a constant bias, but the standard deviation on the monthly basis is much more important. It's 2 to 3 times higher than what we observe on the Aquaterra. So I would say that's not that bad. I mean, but it's more comparable to Navitra than to to MODIS kind of like data set kind of quality. If you look also at the blue and the green is still kind of reasonable for planet, but the blue is definitely very, very, very noisy. So, and large bias. But once again, this was the first attempt to look at the data, and there is a lot of variety of data in the planet world. The first data set I presented was mostly consists mostly of what they called the Dove Classic, which was the early generation instrument. And now we look at a subsequent data set with a larger number of sites, and mainly focusing on the new generation sensor, Super Dove, and the SB called the next generation, which has a 8-band versus the 4-band classic and Super Dove, or also called Dove R. And something I like to point out here is this is the MODIS red band, and this is the MODIS near infrared band in magenta kind of color here. And the green here is the Dove Classic red and near infrared. So I'm glad that we didn't spend too much time on it, because definitely spectrally there's some issue to match, and it's much better with the Super Dove and the next generation. So So in that second data set, longer time period, more sites, and a number of individual planets seen approaching 10,000. So it's quite a job. So here we had several flavor. Like I say, we had the superdove, or also called dove R. So on the superdove, mainly, you could see it looks a slight improvement. I mean, the bias is actually roughly the same, maybe a little worse in the red than before. And looking at the monthly data set, this is the Aqua on a monthly basis, so you could see the pretty stable signal. I mean, almost on average with very, very little variation. With our standard deviation, which is like plus or minus actually 3%, 3 to 4%. And here I don't have the statistic for Terra Aqua because I'm in space. So, and here the 1 year of data analyzed. So pretty much about the same result now, both in the near infrared and in the red. This is the same kind of noise level, which is, like I said before, like 2 to 3 times higher than what we're seeing on Terra Aqua. And also, what's noticeable here is that it seems that we have some systematic time dependence on this calibration, which is not very good. Blue and green. So now for the superdove is better than it was for the Dove Classic, as you could see. Still a pretty important bias, and still degraded performance compared to Aquaterra. And in the green is not too bad. I mean, it's kind of almost like consistent with red and infrared, but the blue is much more problematic. We had a few Dove Classic dataset which filtering on download. I don't know why, but it happened. So we look at the classic data, and it pretty much confirms what we've seen in the previous dataset. And we noticed also that there was some of the one instrument, and let me see which one is it. Okay, it is number 1105, which was pretty much not a true outlier from the constellation. So same thing in the blue and the green as we've seen before. Finally, end up with the Dove next generation. The good news is, like, I mean, although it's a reduced data set, but it looks much better, which is the good news. But what seems to appear now with this next generation data set is that we have a much larger bias, about 10%. But this bias is almost consistent in all wavelength. I mean, it's pretty consistent. So maybe something we can correct for, we can account for. So in summary, I don't want to take too much time. I think, what this data set point out is that you do need, which has not been the case for Planet, a rigorous, what I call a rigorous calibration approach. I mean, have the current correction, temporal monitoring, independent calibration for each instrument. I believe the data set we've been looking at that point, it was roughly calibrated for the whole constellation as an average calibration, I mean, to some extent. Cloud screening I mentioned briefly, but it's really important, and maybe it's something that Planet people needs to pay attention to, because it's very important. I mean, to combine data set, you cannot do without it, and even for a regular time series with one instrument. It's important. So when you have several, it's really important. Also, probably we can improve atmospheric correction, but we need improvement for the planet calibration to bring it to the level that the user community expect with current instrument. We need prior characterization prior to launch. We need calibration while in flight. Probably, even simple in-flight calibration device or something. And so that we can, apply this cross-calibration approach, but it's not really a cross-calibration approach. It's more an evaluation of the cross-calibration, I would say, as much as possible to keep everything independent. We can also try other method that have been used in the past. I mean, looking at the moon, looking at cloud, looking at rayleigh scattering. And everything, of course, need to be documented and peer review and published, so the user community can have traceable information. That's all I have. Thank you very much.
Thank you, Eric. This is very, very detailed with a short period of time. What we're going to do, we're going to hold the questions to the end, so we'll go back with Eric. And so next up will be Gary and Ben, and we're allowing about 15 minutes each, for the geolocation, and then we'll have Alexei for another 15 minutes and have a few minutes for questions. So if Eric, if you want to go through the chat and answer some of the questions that came out for you, that'll be appreciated. If not, we can hold it to the end. So Gary and Ben, take it away.
Bin?
Can you see it like this?
Yes.
Yeah,
Okay.
Perfect.
Good.
Thank
Good.
you.
Okay, so I would like to give an introduction on our work on the geolocation assessment on Planetscope images. First, I will give a brief introduction to all the algorithm we applied, and then I will introduce the assessment result for the reference data and the assessment result to the Planetscope data. So first of all is a brief introduction to the algorithm we applied. The image matching algorithm we pick up is a Pearson cross correlation. That's a pretty popular algorithm. I don't think I need to spend too much time here. Basically, we have a reference data, and as our truth data, which we assume that the geolocation accuracy is better, then at least better than the target image here is the Planetscope data. And then we have a target image. We calculate the cross correlation between the target image and the reference image, and also introduce a shift between these two images. Then we have a cross correlation plate to generated by shift the target image around, and then we pick up where the maximum cross correlation value shows that that's supposed to be the best registration point between two images. And there's another important algorithm is the measurement uncertainties. The matching point estimated from Pearson cross correlation could be in poor quality. So we need some method to reject the poor quality assessment into our final result. And this filter works pretty good. We use it for ghost satellite assessment too. And later in this presentation, you can see how it's working. In this measurement uncertainties, we use the peak sharpness and refine the cross correlation value, and also it's related to image dimension and the contrast, relative contrast between two images and the image itself. And the larger measurement uncertainty value indicates a lower assessment confidence. It means that that should be rejected. So the question is where the threshold. And then currently we are manually determining the threshold. We are developing an automatic method by our group member to eventually we will have an automatic method. And here it shows a prototype how we do this work. The image shows here is a world view image, and the right point here is a grid. Basically, we robust select the matching point over the fine resolution image, and each writing point is a sub indicated the center of the sub window where we will perform a cross correlation matching assessment. And for the planet scoped image assessment, our sub window size is 250 meters by 250 meters, and there's a 150 meters boundary buffer between two sub windows. The first thing we do is not to assess the Planetscope data. Rather than that, we assess the reference data, world view data here. We assess the reference data quality because this definitely will impact our assessment to the Planetscope data. Here shows one example what we do here. We have 3 scenes of data. They are over the same region, and on the literature report, the error in the world views data is 3.5 meters of C90, and the C90 dropped to 5.4 meters for the rectified images. And here we use 3 images to test them. And the right hand side, you can see there's a combination of 2 images. And you can see that there's a mismatch between 2 images. And the lower table shows that use our Maxar to assess the offset between the first image and second image, the first image and the third image, and the second image and the third image. And the last column is what we call the calculated image offset between image 2 and 3. It means that this is not directly assess the image 2 and 3 with our algorithm. Rather than that, we calculate the difference, the offset between 2 images from the assessment result of the first 2 columns, image 1 versus 2, image 1 versus 3, and then we use them to calculate 2 to 3. So you can see that if we look at the whole assessment result, most of the image offset is within what is claimed in the literature is about 2 meters. And if you look at the last 2, the right hand side 2 columns, they are very close. And direct assessment result in east-west direction is 1.52, and our calculated result is 1.3. And on north-south direction is negative 0.6, and calculated is negative 1.2. The difference between these 2 columns actually is our measurement error with this algorithm. So the direct assessment between 2 images, it could be the difference between direct assessment and calculated assessment is that we have 2 assessments, 1 and 2, 1 and 3, and then calculate the assessment of 2 versus 3. So basically, we introduce one more assessment error, measurement error from this algorithm. And you can see that with one more measurement algorithm built on top of this assessment result, the measurement error is still within 1 meter. So this slide basically gave us 2 information. One is the reference data is in good quality, at least for this site, and the other one is the algorithm measurement error is very small. It's within 1 meter. Here is a assessment of the reference in another case, in another site. Unfortunately, in this site, you can see that the east-west result is 8 meters. It's well beyond the literature report accuracy level. And so the image, from the image, you can see that too, the red and the blue, red and the green is from scene 1, and the blue is from scene 2. There's definitely a very large offset. And the takeout from this slide is that the reference image world view need to be assessed by our cross assessment by our algorithm to assess the consistency. And that should be performed for each site before we can use them to assess the Planetscope data. Here is the Planetscope data assessment result. This is one site in New Mexico, and we have about 30 Planetscope image in this site, and we have about 10 worldview image for this site too. And this is result from all the Planetscope data assessed against all the worldview data. And the left-hand side plot shows the offset versus measurement uncertainties. This is the I-axis. Please note that the x-axis is not measurement uncertainty, is 1 over MUS, 1 over measurement uncertainties. That's why if you get a larger value, you get actually better quality. It's not actually it's not a measurement uncertainty itself. It's 1 over measurement uncertainties. And from left-hand side is when you see there's a spread out the estimate offset in XR or offset, it means that there's a lower measurement, lower accuracy, and we are trying to reject to filter out these poor quality measurements. The red line here shows the filter we selected for this site, and the right-hand side table shows the result before filtering and after filter. So before filtering the result, we have a large amount of chip numbers. The small subset window, as I showed at the beginning of this talk, each subset window is 1 chip. We call it 1 chip. It's more than 55,000 chip numbers. And the estimated offset in both directions is still pretty good. It's about 2.5 and 0.08. After filtering the result, we can see that the chip number dropped to 8,000. They are all good quality measurements, has a more reliable result than before. And the east-west offset it changed to increase a little bit to 4.2, and the north-south estimate it changed to the other direction, so it changed to negative 0.8. The change is within 2 meters.
Hey, Ben, I'll remind you, you got about 5 more minutes.
Okay.
So we can get Alexei on. All right,
I only have 3 more slides. I'm quick.
Okay, thank you.
Yeah. And the planet, this is for another side, Singapore side. This side has the west worldview result, worldview image. They are not in good. They are not agree with each other in good quality. So we only use single worldview image to assess against all the planet data. And left-hand side is from one single worldview image. Right-hand side is from another worldview single image. So you can see the estimate offset primary difference is on east-west direction, and is corresponding to the worldview image offset between the offset between 2 worldview images. And this shows that the Planetscope data actually has a better consistency in this set. We also perform actually, we didn't show it here. We also actually perform all the assessment over different continents, and we have global assessment over 30 sites. And here is one of the sites we performed the temporal stability. And this site is in United States. And here the table lists the time, the temporal, the time when the image occurred, and also the assess the mean and the celebration for this image. And you can see that this the Planetscope data had very consistent geolocation accuracy. And from different time, they have almost the same east-west and north-south offset against a single west view image. So here's the summary. The algorithms can accurately assess the relative geolocation accuracy. And we do need a filter to remove the poor quality assessment. And the world view image should go through a quality check before being applied as a reference image. And the geolocation and consistency for the testing Planetscope image is good. That's all.
Thank you, Ben. Did a record time there. So again, if you have questions with Ben, you can go ahead and put them in the chat, and so that we can see if we have a little bit of time left. We can go ahead and move on to Alexei.
Thank you, Alfreda. Do you see my mouse?
Yes, we can.
Nice. Good afternoon, everyone. And as you can see from the title, we not just evaluate calibration, but we, oopsie daisy, it moves forward. Where we do a real calibration, full calibration of the Maxar constellation. Previously, it was a digital globe, so don't get confused. I will use them interchangeably. Here's our team. This is at the bottom, and we work closely with a group of geometers. So whenever we talk about science processing, of course, we need stable and reliable calibration. So one of the main tasks is detection and characterization of the long-term trends. And if we have multiple sensors on orbit, which is situation with current commercial satellite vendors, we need to make sure that they all effectively cross-calibrated to a single baseline. And that would allow us to significantly improve, let's say, temporal frequency in our processing, which is crucial in most of disciplines. So to do this work, we adapted our MODIS calibration technique, which we developed over a decade ago, sort of to address a small crisis in MODIS collection 5 data set when science products showed rather significant trends, and it was traced to calibration trending. So, and here's the idea, what we do. We are focusing on stable, CEO's recommended desert calibration sites, and one of them is Libya 4, specifically used in this work. It practically never rains in that area, so it remains stable. It's pretty homogeneous at relatively large scale. So this is what we do. We perform our Mayak retrievals for MODIS in this case, which provides a very reliable cloud mass, cloud shadows, aerosol retrieval, water vapor, surface reflectance, BRDF in all spectral bands, etc. Next, we use that information to recompute expected top of atmosphere reflectance, but for the fixed view geometry, nadir view and sun angle typical of those latitudes. So, and if you look at the top right, you can see that effectively this geometric normalization allows to beat down the variability in the measured signal by a factor of 3 to 5. So once we normalized, here you can see on the left, we see pretty constrained image, and it's relatively easy to detect trend in those data. And once we detrend the data, and then do the same for both Terra and Aqua, which you can see on this plot, we start seeing the difference in the calibration. This is at the top of atmosphere. Therefore, a simple ratio in that case provides us the cross-calibration coefficient. In that case, we applied, of course, to Terra to cross-calibrate it to Aqua, as Aqua has been the newer, more stable, more well-behaved sensor. And still, it remains the, I would say, the flagship of the entire EOS program, which has generated excellent quality climate data records. Now, if we apply all of that calibration to both Terra and Aqua, effectively they become a single sensor, which you can see here at the bottom. And by the way, if you heard Eric's talk, those very nice scatter plots, Terra versus Aqua, it is the result of application of this technique and calibration, cross-calibration coefficients at the L1B processing, which was used in the standard MODIS line discipline processing starting in collection 6. I should also mention that we performed the same analysis for the VIRS SNPP and J1, cross-calibrated it to MODIS Aqua, and therefore very soon a consistent set of data effectively extending our CDR record from MODIS into VIRS will be generated. So how do we apply the same technique to Maxar? Of course, we are using our MAYAC MODIS ancillary dataset, atmospheric aerosol, column water vapor, and spectral BRDF at 1 kilometer resolution. Now, there are some issues, of course. The frame size or SWOT for the digital globe sensor is small, about 17 kilometers. So effectively, there is a low spatial overlap among those high-resolution images. And you can see one example here where the left image shows the MODIS style effectively covering the Libya desert here on the top left. And the inset shows the larger 100 by 100 square kilometer areas, which we selected as a larger calibration target. The Libya 4 is right at the center here. And on the right, you see what happens with the Maxar data. We have very little overlap. We would like data to be here at the center, whereas other data somewhere else within that 100-kilometer area. So in that case, we do both. We're using our MODIS BRDF information to do both geometric normalization and also what I call spatial transfer. So we take data obtained in this region, for example, we use MODIS BRDF and take ratio of our MODIS BRDF at closest spectral channel between this location and this location, and that gives us the what I call spatial transfer coefficient. That allows us to effectively bring all the observations to one point. Now, what do we get after that? Here's an example for the WorldView 2 data in the RGB and infrared band. And the blue lines here show results with geometric normalization. And by the way, the orange lines show results without geometric normalization. So you can see that that normalization is really crucial. Otherwise, you can really get wild data. So moving further, in case of cross-calibrating Terra to Aqua, it was easy because we have effectively the same sensor and with the same relative spectral response. So a simple ratio of those provide cross-calibration gain factor. Now, in this case, sensors for different Maxar instruments, that they have different RSRs, and not only in central wavelengths, but also in the shape of the spectral response function. Plus, all of them, of course, are different from MODIS Aqua. And Aqua, we selected Aqua to be a reference sensor to cross-calibrate all Maxar data to Aqua. So, what do we do in this case? We are using DESIS data. This is German DLR Earth Sensor Imaging Spectrometer. It has been flying on the International Space Station since 2018. It covers the visible to infrared range from 400 to 1000 nanometers with strong high spectral sampling and resolution of 3.5 nanometers. And it's Landsat-like spatial resolution, 30-meter scale and about 30 kilometers SWOT. So we've been collecting those data. The program has been collecting for us. We have pretty large statistics. And this is one of the examples of the averaged DESIS spectra over 5 by 5 kilometer central area over the Libya 4 site. And as a reference, here you can see Schiamaki data. Schiamaki comes at 1 degree resolution, so about 105 kilometers. So you see some difference. And the goal here is effectively to aggregate that spectra with the RSR or specific sensor That would give us effective reflectance of the surface at this wavelength. And we do the same for the MODIS Aqua. So ratio of those would allow us to sort of transfer from the Maxar wavelength of any sensor to MODIS Aqua. And then we do top of atmosphere calculations for those Maxar sensors, but at the Aqua wavelength. And therefore, at the top of atmosphere, we can do apple-to-apple comparisons with Aqua to get the cross-calibration gain coefficients. And here's one of the examples for GOI in RGB and infrared bands. So what is shown here is detrended data, already detrended, and the red line and points show Aqua data. We have high very dense time series, very nice. Now blue lines show original data, once again detrended and geometrically normalized. And the red shows spectrally shifted GOI data to match Aqua. So we will be comparing black and red. And ratio of those provides cross-calibration coefficient. As you can see in blue, especially in the blue, they're practically identical. In green and infrared, they're pretty close. There is a certain difference, relatively large, in the red. So if we summarize all of these results, these are data for the detrending, these are data for the cross-calibration. What we can say, if you compare the trends for Maxar sensors, compare them to residual trends in both MODIS Terra and Aqua, you will see that they are a factor of 2 to 3 higher. So the data shown as trend per year per unit reflectance. So how do we interpret this data? For instance, for the worldview 2, in the course of 10 years, and at the level of reflectance, say 50%, the trend will result in the signal change of about 1% in the direction of the increase. So, and finally, here we have characterization of statistical significance. So anyways, cross-calibration coefficients. For the quick bird, we have very low statistics. So you see the data sort of not matching the other sensors, and we don't call them reliable. They're just shown for the completeness of the picture. But as a summary, what we can say that all Maxar sensors are pretty well calibrated and are within 2 to 3% from each other. Generally, they are systematically higher than Aqua. And only worldview 3 in the blue band is practically the same as Aqua and slightly lower. But all other sensors are within this range from MODIS Aqua. The biggest difference is in the red. All of them are higher than Aqua once again, but in the red, the difference is from 7 to 8%. So just a couple more slides as a conclusion. Generally, this has been fun. Our main interest is, of course, atmospheric correction, which we do for MODIS, for the VIRS, for the geostationary. It's also in the Landsat. Very high resolution data are very interesting application. So in this case, we're relying on our Mayak MODIS ancillary data. And the quality of all products is really high. In our latest published evaluation, where we compared the high quality surface reflectance data from Mayak with Modo 9 product, we've seen that Mayak provides from 5 to 25% more high quality data. And the biggest difference is in the very cloudy areas and areas with high resolve optical thickness. Like China, Southeast Asia, those regions, developing regions as well. column water vapor, it has always been great accuracy. AUD comes at high 1 kilometer resolution and really high accuracy. And in collection 6.1, you can see here global statistics. We further improved the accuracy of aerosol, and pretty significantly, you can compare the first two lines. So I won't go into the detail, but I should say that the ancillary Maya cloud mask and aerosol have been successfully used to screen the good quality conditions for very high resolution data to select cases with low average cloudiness and low aerosol. That's case where we have both good atmospheric correction and generally good processing. And of course, we have the both atmospheric correction with BRDF normalization, and I'd like to conclude with a couple examples. Somewhere in Madagascar, couple pictures. On the left, you see the top of atmosphere. On the right, the fully atmospheric correction image. Thank you.
Thank you, Alexei. We do have a few questions in the chat, and I believe they have been answered. I know Eric answered some, and Ben was answering those two that were coming in. Do anyone quickly have a question for Alexei? We definitely will make these slides available to everyone after we collect everything. For all of the Lunch and Learns, we have them on the CSDA website, so you can go back and look at them later. Also, I'd like to put in a plug for probably about another time during the summer. We will have another Lunch and Learn with some more of our SMEs that are part of the SUSTAIN program. Will give us some talk on the work that they have been doing with respect to data quality. For example, the RO. We could be looking at some Planet Stereo and possibly some work that we have been doing on the modeling side. So keep a lookout of that. And the meeting has been recorded, so we will have that also available to everyone. So do anyone have any quick comments or quick questions? Fritz, look like you're unmuted now.
I just want to say thank you very much to the presenters. It was very nicely done.
Yes, and thank you, Eric and Gary and Ben and Alexei for putting this together. This is something that I wanted to do for a while, and we will continue to keep the community informed of our progress as we move on. So we're about 1 minute over. And again, thank everyone for your time, and we appreciate the presenters again for these excellent presentations.
Thank you all.
Thank you, everyone.
Thank you.
Yes, we will provide access to the slides.